Thank you. And it's my great honor to give this presentation here. And my topic is the copolymerized ionic gel for DMMP sensing from material to multi-type sensor applications. And I'm Yuan from the Xi'an Jiaotong University, China. And here is my outline, and it contains 4 aspects. The first one is the research background. Well, the application of toxic and harmful gas detection exists in every aspects of our lives, including the industrial gas detection and hazard chemical gas detection. For me, my target gas, DMMP, is a kind of VOC gas and have toxic and risk for human beings, and it sometimes be used as the simulants for the chemical welfare agents for some scientific research. So it can also cause the atmospheric pollutions. And in addition, the detection of DMMP should often be done in complex scans. So there's some demands, for example, the low concentration and the fast response time. And another important thing is the portable and the low power consumption for the detection systems. And some traditional methods like the AMS and GCMS method have problems in high power consumption, and the PID equipment sometimes is poor in selectivity. So probably the micro gas sensors with low cost and the small size and low power consumptions can probably solve these problems. For example, there are some examples. For the first one is a joint detector M4. It equips with multi-type surface acoustic wave sensors with different sensor films and with very small size to detect many target gas within 10 minutes. And the next one, for example, the MEMS and CMOS ENOS, it integrated 4 source sensors with polymer sensitive films with a front-end integrated circuit and packaged together with very small size. It can detect 1 ppm toluene vapor, and to be honest, it probably the macro gas sensors and combined with some intelligent sampling and processing circuit is a good choice to meet the need of the future applications in some smart gas detecting systems. So the second part, I want to introduce a brief introduction on the ionic gel-based DMMP sensing materials we prepared in our lab. So the ionic gel consists of the 4 components. The first is the ionic liquid, and the second one is the polymer. Also, we add some sensitive groups to the materials to get the DMMP sensing performance, and also the photo initiator. We mix them together uniformly under the ultrasound and use UV light to polymerize it. And we expose to the UV light, the carbon-carbon double bond open and polymerize together to show this nano shrink on the surface, showing this SEM image. And when I get this ionic gel materials, I use the material to prepare the different type of micro gas sensors for DMMP sensing. There are 3 different type of sensors we used in our lab. The first one is the surface acoustic wave and also the flexible sensor. And we also used it for the gate electric of the field effect transistors. There are 3 different types. The first one is the surface acoustic wave. And for this type of device, it is prepared on the piezoelectric substrate with an output and input interdigital transducers on the different side. For the input port, there occurs electrical acoustic conversion, which means that in the input port, it can convert the high frequency input electrical signals to the acoustic waves, and in the output side, there occurs acoustic and electric conversion to convert back this surface acoustic wave into electric signals. In this case, we put our sensor films in the sensor region, which is in the middle of this device. Then we can get the sensor information from detecting the amplitude or the phase of the output signals. Our device working in the 152 megahertz. And this slide shows how we prepare the ionic gel on our salt device. We firstly pre-treated the soil substrate with the oxygen plasma to increase the hydrophilicity, and we use another corn substrate to pre-treat it with HMDS to make it hydrophobic. And then we drop case our onyx gel on the soil device and cover the corn substrate on it. And then we use the UV light to polymerize them and take the corn substrate off. So in the right side of the slide, you can see that the polymerized onyx gel on the soil device have the average thickness of 0.7 micrometers. And this is the sensor performance of our soil device prepared on this prepared on the onyx gel for DMMP sensing. It has LDO of around 200 ppb and also good selectivity. The sensitivity and the selectivity mainly comes from the hydrogen bond occurs between the DMMP and HFPA. HFPA is the sensor group we added in our onyx gel when we synthesize these materials. And in this slide, we also use the onyx gel to prepare the flexible sensor. We spin coating the onyx gel on the flexible PN substrate, and when exposed to the UV light, we add a shadow mask behind the substrate, and therefore we can prepare the patterned sensor film like in the figure you show in the right of the slide. And the onyx gel prepared on the flexible substrate has an average thickness of 3 micrometers. And because of the ionic liquid in the material system, we can form the electric double layer at the interface of the electrode. So this type of sensor can be worked into the two different modes, for the capacitor mode and the resistance mode. And the green line here is the response curves we measured under the capacitor mode, and the blue line is in the resistance mode. And all of them shows good response and selectivity, and also the LOD of this device is around 100 ppb. And the third one is the field effect transistor type sensor. As described in the last slide, the onyx gel can be used as the capacitor, so it can also be used as the dielectric of the field effect transistor. For this slide, we use the carbon nanotube to build a transistor, and it is a double gate transistor which has the back gate of the traditional hafnium dioxide back gate, and we use the onyx gel as a top gate to sense materials, to sense DMMP gas. Then this is the structure of our device. It has a double gate, and in this slide, the blue curve shows the transfer curve of our device. It has the full magnitude of ratio. And also it's very interesting that the sensor shows obviously gate turnable sensitive properties, which means that the sensitivity of our sensor can be turned under different gate bias. So it is very interesting for us to explore some future applications and the future investigations. And for the last part, I want to give the introduction of the applications of the sensor is mainly focused on the soil device we introduced in the very beginning, because it is probably the most reliable one among these three type sensors in state of art. So the detection and the detection of the soil sensors usually be done in the lab through this way. However, it's very heavy and complex and cannot bring out of the lab. So we have to self-design a radar circuit. Among these three methods, we choose to directly measure the phase shifting of the soil sensor, because probably it is a high response and much easier to design for us. This is the layout of the FPGA-based detection system that we prepared from our soil device, and also the layout of the PCB board. It is based on an FPGA chip and also have a high-speed DDS to generate high-frequency signals to drive our soil sensor. We add two soil sensors here, and also the commercial SO2 sensor. And also the phase detector to directly measure the phase shifting of our soil sensors, and the ADC to sampling the signals to send back to the FPGA for further processing. And we also use the Qiang algorithms to distinguish the alarm situations and the safety situations of this system. So this is also called the intelligent detection systems. And for the last one, temperature and humidity interference must be concerned for all the sensors working in room temperature, because the interferences of the temperature and humidity may cause very serious false alarm for the sensors, and they can also cause the very serious shifting of your sensor's baseline. You can see in this slide. For us, we use the very simple and practical method. We add humidity and temperature sensor in our detecting system. And we use some algorithms to calibrate it. You can see that in the green lines, in the top figure, after calibration, the baseline of the sensor is very smooth. So, and then we package our system together and get out of the lab to do some measurement. The system works very well. And so this is all my presentation, and thank you for your listening.